So hello everybody, so I'll give a little introductional tutorial today about MNHN-Tree-Tools. And so the big question, probably what you'll want to know, is what is MNHN-Tree-Tools? And basically it's a tool to perform phylogenetics and has some extended applications, so it's not just about phylogenetics, but it can do a lot of things. And so basically, first of all, well, what can you do with it? You can cluster almost any data set of nucleic sequences, which gives you, so it's density-based clustering, is basically a TBScan algorithm, further augmented here for phylogenetic inference, let's say it like this. Yeah, so you can build the tree of life from 16S or 18S ribosome sequences. We have shown this in the wild, so this is published data. We have shown that we can do this. We also did this with COVID-19 sequences. This is in a tutorial which has landed on a preprint server, so you also can read this. That's not part of the talk today, but just to tell you that everything that this is all stuff that you can do with our tools, the tools that we have developed. So what else can you do? So basically you can calculate chimeras from nucleic sequences. We will see this in today's talk. You can perform principal component analysis on your sequences. So you can project your sequences into principal component space and do clustering there and do tree interference in your principal component space. But you can also do, of course, very simple tasks. So like duplicate removal, enzyme digestion. If you have a FASTA file, if you want to digest a chromosome with an enzyme, we have a tool for that. You can perform a consensus calculation. We have a tool for that across all the sequences that are in your FASTA file. And basically, MNHN-Tree-Tools is, besides all these tools, well, also an API for the rapid creation of algorithms that you can apply onto FASTA files. So, well, we have a not 100 but a 96-page manual, I guess, about MNHN-Tree-Tools. We have published an article about it, which you can find over here in Bioinformatics, which basically just gives you a brief overview about our algorithm. We also have a website, so more information than actually in the article. There's a supplement in the article, of course, which is pretty large. More information you get on our website. So let's just fire this up quickly here in our web browser. So if you go here to MNHN-Tree-Tools, we see here, well, here you can access the code. You get to the Git repository where the code is basically stored. You have a link to the article, we have a link to the algorithmic supplement, and we have here, of course, the manual, which is in detail and which gives you detail about all the tools that you can find in MNHN-Tree-Tools. So just to bring this up, so as you see here, we have here a plethora of tools that you can use on FASTA files, so which are all outlined here, and which are outlined in detail with the algorithm and the implementation and the file that you're implemented if you want to continue to develop them, or if you want to dive into the code of the tools. So far so good. Just to show you around where you can find stuff. So the website is very simple. It's treetools, myname.hashcat.net, where you basically find all this stuff. So how does this work? What does Tree-Tools do? Besides getting you this overview here. So basically what you really need is a FASTA file. So you need a database where you have all your sequences inside, so one single file that contains all the sequences. Yeah? What we do in most of the cases in our workflow in order to generate the phylogenetic tree from those FASTA files is we re-express these FASTA files as k-mer frequency vectors. And then, so what is this K-mer frequency vectors? What are these K-mer frequency vectors? So you have a little sequence here, and I want to find two mers inside that sequence. Yeah? So two mers, this means that these are all possible amino acid combinations of two. So if this would be 3, this would be all possible combinations of 3 amino acids. This would be 4, all possible combinations of 4 amino acids. Yeah? Why do we do this? We do this in order to get those sequences length independent. So if your sequence, if you have sequences of 3000 basis pairs, for instance, and then you have one which is 3050, one which is 2972 basis pairs, well, in order to compare them, a very efficient method is to use K-mers. Yeah? You want to choose K so that all the information basically is kept inside your K-mer representation, which means that well, for a short sequence, of course, here I have 16 components, so I'm looking up 16 pairs in this case, because it's 2. If it would be 3, well, it would not be 16, but it would be to the power of 4 more. So we see here that if I'm looking up, for example, the AA amino acid sequence in our sequence, we don't find it, so it's 0. If we look here at AC, well, AC we find 1, so we put 1. Yeah. AG, we don't find AG, we find, for example, CT, so we have 1 here, and we find DA, 1 here, yeah? And we also should find CC, so CC we find at 2 positions, so at this position here and at the next position, so this is twice counted then, no? Yeah, you basically get the idea. Normally you don't use 2 because your sequences are longer than this. You use 3, 4, 5, about 4, 5. Yeah, let's say like this. For the COVID sequences, we went up to 7. COVID sequences are 30,000 basis pairs long. If you go up here to 7, you get here 16,000 components, so it's reasonable to use them in order to study them. If you go up to 8, you will have difficulties to continue the calculations, because if you then perform PCA and you have, already at 7 you have 16,000 by 16,000 matrices, so you need to have performant computers in order to diagonalize them and in order to calculate eigenvalues and things like that. Just think how many components do I have, how long is my sequence, how much information can I capture with that, with 16,000 vector components as well as K-mer counts. You can go up, I would say, up over 60,000 basis pairs, but you have to you really have to think about how much information do I retain in my representation. That's basically the story here, yeah. And of course you're limited by computational power, because K8 will be very difficult to compute with reasonable machines. Yeah, let's say like this. So, okay. You have your K-mer representation of your fastest sequences right now. Once we have these, we want to do, of course, dimensionality reduction, because you don't want to calculate distances between 16,000 and 16,000 vectors. Yeah? This is a high-dimensional problem. You have this curse of dimensionality. You can look it up on the internet. It's a big deal. You want to live in a low-dimensional space when you want to compare vectors, to be honest. So there are several tools that make you compare in high-dimensional space vectors. It's very inefficient. It has its drawbacks. I don't want to go into details here. This is a mathematical problem. We want to show you here MNHN-Tree-Tools, how it works, just to get you going and to get you to the basics. But if you want to know why we do dimensional reduction, look up the curse of dimensionality or hubness, you will find it out. So basically there are two ways to do this. So either you do it with an autoencoder, so this tested is not published, is not shown in the manual, you can do it. But here, also for the sake of this tutorial, we will stay with the principal component analysis method. Okay. Principal component analysis, so the k-mares grow with 4 to the k power, so 5 mares, you're already at 1024 vector components. The principal component analysis basically allows us to reduce this to a reasonable number. A reasonable number for, in our case, would be 7 dimensions, for instance, so that the algorithms that we then afterwards use won't fail, because we also perform, of course, tree building, because we want to get phylogenetic insights into our data. And then it also serves kind of as a feature selection method, because it selects, of course, the k-mares which have the highest variance in our data set. Think about this, variance feature selection. It's not something else different, it's just variance feature selection. Okay, so the basic idea behind PCA, for those who are more from a biologist side and less from a statistical side, is that if you have a high dimensional data set, and here, well, very easy shown here for 2-dimensional data set that we want to reduce to a 1-dimensional data set, we calculate these what is called these principal components. So these are basically vectors in these directions that you see here, and these are orthogonal, so they are intrinsic of the dataset. They are calculated from the eigenvalues and the eigenvectors of the covariance matrix. That's the way it's done. But just to see, if you have a data set like this, you will probably get out, well, vectors like these, and what you see here is that this vector here is very small compared to this vector, so you have a way higher variance in this direction than you have in this direction. And basically you get an orthogonal data set out of it, where the first vectors are the highest variance vectors. And so what you can do here is, well, you can say, okay, in order to transform this 2-dimensional data set in a 1-dimensional vector set, well, I transform my coordinate system into this coordinate system, which is doable because this is just an orthogonal basis, just as our Euclidean axis here. And from this data set, I basically I just remove the second coordinate. Now, once the second coordinate is gone, well, I'm just in one coordinate, and as this is the coordinate with the highest variance, it is a reasonable choice. So we do this with our data set, and this allows us to project it, for instance, into a 2-dimensional space. So here we have a 2-dimensional representation of our 1024-dimensional data set, and we calculate here the densities in this 2-dimensional data set. This is something that we can do. So basically we make here a grid, and in this grid, so in each little square, you count the number of sequences that fall in there, and you can generate a graph like this. What I want to show you here is that you can get a 2-dimensional representation. In this case, first 3-dimensional linearization because of the density, but you can this is a 2-dimensional image. We will see this then in the tutorial of your high-dimensional data set, and you can already well perform clustering with this, because if I zoom in here, so let's make this a bit bigger. What did I do? If I make this a bit bigger here, we see that we have little, oh my god, that's way too fast. We have little mountains in here, and we can say, well, this here is a special cluster. This might be one species, this might be another species, this might be another species. And here we have something completely different. It's very small, but we have something. This might be another species or something like this. And one of the ideas behind, just to motivate it, one of the ideas behind the algorithm here is that old sequences are very diffuse. Sequences that have appeared more recently in the evolutionary history are closer together and are more dense in the sequence space. Yeah, so one of the core ideas about this algorithm is the density. Yeah, and we vary the density in order to understand the evolutionary history. Yeah, so if you have this diagram here with the density of sequences in a two-dimensional space, sorry for that it reloads here, this was not intentional, but let's make this a bit bigger, yeah? Then you probably won't see me in the little window, but not so beautiful, so maybe it doesn't matter, yeah? So, I'm still here, don't worry. So, if we put in here a plane, yeah, on the, let's say on the bottom, yeah, we are like in the zero space where we have all the sequences covered, yeah. And if I move this plane up, yeah, I basically cut the mountains apart, yeah, and then I'm basically in a more dense space, and these cut about mountains are later species that have emerged from the sea of diffused sequences, which are more at the bottom. Yeah, one can understand it maybe like this. Yeah, this is one way to understand it. Okay, so besides this PCA, you can also use this autoencoder. We will skip this here for this tutorial. I will just fit this to the width. Yeah, okay, so that you see this. And so we have done the K-mares, we have done the PCA. Right now, well, we have our sequence space. Right now the big question is, how do we infer phylogenetics, or how do we infer trees? Huh? How do we build trees? And so we have this sequence space here. Of course, we're our PGA projected, and just keep this image here in mind. But further, so at the heart of all of this is what we call the TBScan algorithm. So the TBScan algorithm hasn't been invented by us; it's a very old algorithm. But we have modified the whole story. Because the TBScan algorithm runs once at a given density, and we just vary this density in order to perform phylogenetic inference. And so what does the TBScan algorithm? So if I have a data set, so imagine points in 3D space, let's say it like this, yeah? And then you have clouds of a given density, and you say, okay, I want to have all the ensembles, yeah, which are connected and which share a density at least higher than a given density. Yeah? This is what TBScan finds you. Yeah? And, well, how does this work? So basically the density is given by volume, this volume is given by radius. So you have a radius which gives you a sphere, and then you define the volume, well, by the number of data points, sequences in our case, that you find within this sphere. Okay, sphere, number of objects inside gives you density. Okay, yeah, a fixed density. And how does this work? So we have our radius epsilon. Basically it says, well, okay, let's perform a run with at least three points within this radius. So 3 points within a given volume gives us the density, yeah? And so basically it says, okay, let's start at this point. Okay, I don't find 3 points around this point, so nothing. Try another point, try another point, and I find, well, wow, 5 points around my point. This is a cluster. This is the beginning of a cluster. And so I try and the next point, this point I just find 2 around it, so nothing, yeah? But I tried this one, I find 3 around it, so, and it's part of this other point, so I extend the cluster, and this way you find connected dense ensembles, yeah? But that's the TBScan algorithm. It's not our algorithm. That is kind of the core of our algorithm, but that's not what we do. What we do, I mean, that's what we do, but that's a little part of it. Now, what we do then is more deliberate. So, using this algorithm, you find that actually, okay, these points, they are not part of a cluster because they're too diffuse, but these are dense enough so that they join the cluster, and we find this cluster over here. These 2 points here in the middle, they're too diffuse, they don't form anything, and we find a little cluster over here with 2 points which are too far outside, so they are outside of the density limit. Yeah? Okay. Yeah. And well, the stuff is, if we increase epsilon, we will see that these clusters will grow, and eventually we will just get one cluster one day. Yeah, because what happens if I increase the epsilon? Well, if I increase the epsilon, it means that the sphere gets larger, yeah? The volume gets larger, but I keep the same number of points, so the density decreases, and I get more diffuse clusters, and the more diffuse cluster has to be in some way, if all our ideas about evolution here work right, be more diffuse, more ancient in history, let's say it like this. Okay, so once we have this, we come back to our diagram. So let's imagine these are the sequences that we have obtained, the image that we have obtained from our principal component analysis, dimensionally reduced image. This is our sequence space. Okay? Now comes our magic. It's the change in epsilon here. So we perform TBScan once. Perform TBScan once with a very small epsilon. With the very small epsilon, we find only very dense clusters. Yeah? So we find the purple dataset, we find the green dataset, and we find the orange dataset. But we don't find the blue dataset or the red dataset yet. So what we do then is we increase epsilon. Okay, increase epsilon, and we find, well, a blue dataset, but the blue dataset actually contains, of course, because it's the lower limit of the density that counts here, yeah, it contains the violet, I didn't say purple, violet, whatever you want, and the green part. So this is all blue, yeah, and we find a new cluster, the red one, and the orange we already had, but it didn't increase whatsoever. Yeah? Okay, so what do we know from this? So there has existed, one can say it like this, there has existed some kind of species, phenotype, whatever you want, yeah? It was more ancient. It was ancient to the purple, rose, that we call this, and green data sets. And this blue data set has in some kind of way in evolutionary history generated these purple and green data sets. Yeah? So in theory, we could calculate the mean of these points, find a point in the middle, and say this is an ancient species, something like this, ancient phenotype. Huh? Okay. Yeah. And we find these new data sets, and basically we can then say this is here the key, that the blue species, phenotype, whatever you call it, is more ancient than the green and the purple, which have been generated by this blue at a certain point. Yeah, that's how it works. And the density difference, so the difference from this violet green to the blue, yeah, can be the larger of these traces, or the longer of the length of these traces here when we draw the tree. Yeah? And so we can even get the history, a temporal history, how long did it take, or how much did it diffuse from here to here. Yeah. Okay. So this is what we call adaptive clustering, or tree building. So we take a given density, then we take another given density, we see how the clusters are imbricated into each other, and we build a tree from it. This is our phylogenetic tree. Yeah. People that criticize that, this can be criticized. This is statistically it's working. Yeah, you can look it up in our article, in our algorithmic supplement. We have described the theory around it, up to what kind of limits this might work, and this does work. Yeah, of course it's not perfect, but it works up to certain limits that are described in the algorithmic supplement, and it works for millions of sequences, which is the interesting story around this, because this allows you to not perfectly generate phylogenetic trees, but at least have a guidance and an idea of the phylogenetics going on in your dataset. Yeah. So you can use different distances. You could use the K-MI distance directly. I don't think it's a good idea, but we have implemented it, and you can do it without performing PCA. Yeah? In L1, this is the Manhattan distance, or in the Euclidean distance. You can do this, as I will explain it here in this tutorial, with the PCA in L1 and L2. And you can do it with the autoencoder, we won't talk about this, and you can do it with the Smith-Waterman distance. The Smith-Waterman distance has the advantage that it works at least not as good as K-MI plus PCA, but it's more intuitive, because you know exactly the distance corresponds really to changes in the sequence. Yeah, so the distance really is a multiple of the single point mutations or insertions and deletions. Yeah? And the Smith-Waterman distance is basically an alignment distance which allows you to come across this problem of different sequence length without calculating the chimeras. You don't perform alignment, to be truly honest. You just calculate the distance. Yeah, the distance. What would I need to do? How many mutations do I need, and how many insertions or deletions do I need in order to align my sequence to the other sequence? That's basically what the Smith-Waterman distance does. Yeah. And of course you can use this distance as an epsilon radius and perform the whole algorithm that I've shown you above. Yeah? Okay, so we talked already about this tree building algorithm, so with it here in detail. So you start basically with a high density, small epsilon. You search for clusters, you increase your epsilon, you come to a less density, and you do this until you find a new less clusters than you find here. Yeah? And then you compare, and then you build. This is the way it builds the tree. What is important is that this here is in the algorithm, the way it's implemented, this is monotonic. So if in the next step you find the same number of clusters, it throws it away. It just start to rebuild it if it finds less clusters in the next step than before. Yeah, so you have to choose decent starting parameters, but we will talk about this during the tree building stuff. So we applied this to alpha satellites. This is basically what it was developed for. I won't go into details here. What is way more important is the tree of life. So we compared this to the tree of life from the silver dataset. So the group silver, I don't have it here, but we will of course cite them, yeah, as good scientists do, because this is the silver tree of life. Yeah. Sorry for that. No, that's not what it is. It's silver, like Latin and tree, and they have their project where they basically, this is the project that ARP Silver, the E project, where they basically have experts, so first programs and then experts which create these trees, and you have a data set of 2 million sequences of the 16S and 18S ribosomes, and from this you can create a tree, and they create a tree by hand in the final steps. Yeah, and we do it here fully automatic, and we can do this in less than a week. We get this full tree here, and we can distinguish different subspecies, and if we compare it to the annotation of the tree that they produce, we find that we are rather, let's say, up to certain limits, of course, rather correct with what they get out of their tree. This makes us very proud of our algorithm. So also very interesting is, of course, that this tree corresponds to this PCA image, of course, as we talked about before. Yeah. Basically, if you perform this here and you say, okay, this is the C2 region and this is the C1 region, so you see here that you have the C2 island here, where you have very little sequences behind, so this doesn't perform subclusters, but here you have the C1 island, and of course you have all these little peaks, and so you get all different species out of here, yeah, out of the C1 island. Yeah. It's just to get you a little image about what's going on. Of course, this isn't performed in 2 dimensions, it's performed in 7, 8, 9, whatever dimensions you want. Yeah. Okay. I advise you to use 7 dimensions, but that's the way it works. And so, what are the tree properties that we have here? I will show this to you in your tutorial. So each node is a cluster in this tree. So this means each node you can actually identify the sequences that are in these nodes. Nothing just the tree. We don't just tree the tree, but it's real purpose here. Yeah. So from the outside to the inside, when you go from the outside of the tree to the inside, of course, dense objects, dense clusters are on the outside of the tree. The more you get inside, the more diffuse your dataset gets, the less density you're searching for. Yeah. Very dispersed clusters are at the root of the tree, basically the origin of life, if you want to. It's diffused during time, during evolution. That's the way it is. And the tree length, it can correspond to the density change. Yeah, I'm not sure if I will show you this in the tutorial, but you can program it the way that the tree length here corresponds to the density change. And from this density change, well, if you have a reference data set, you can infer you can relate the density change to the millions of years that have passed, in this tree of life, for instance. Yeah. Okay, and then so this was the inference of evolution distance, just what I said before. Yeah. And of course all the sequences for each node are accessible. I mean, it's not, you can't click on it, but with command line tools that are very efficient, I hope, that I programmed, you will see that you can access all these, and that you have a tree annotated, and it doesn't look as nice as this if you put the annotations on it, but for each node you get numbers that tell you where are your sequences and which sequences are right here at the tree, if you want to. Okay, so let's get started. Let's get through all this. Let's get practical. So I fire up a terminal. This is a Unix machine. This is basically what I ask you to have. So you can do this probably on Windows with your subsystem, for Linux, whatever they have. Use a Unix, a POSIX machine. This works. That's the way it is. So how do we get Tree-Tools? How do we install it? So we go here to the Tree-Tools website. And you have here a little description how you install it. So I will show you here the Ubuntu version. I'm not on an Ubuntu system, I'm on a Gentoo system, but never mind. So if you, for those who are experienced on Unix systems, they probably know that for all these packages that are listed up here, they will find them in their own package repository. There's nothing special there. These are pretty standard packages. Might be more complicated for this POCL, for this stuff here back on the back, but basically what you want to have is an OpenCL implementation on your system if you want to use the Smith-Waterman stuff. Okay, you can use just the standard implementation that is here. If you have an NVIDIA graphics card or whatever, just leave this out. You probably will have it installed. If you don't have it installed, put it in there. If you just want to get the basic stuff running, if you just want to do the tutorial, if you just want to get running, just copy and paste this into the terminal and hit enter. If you're on an Ubuntu, Debian, Linux Mint system, anything that is step-based, this should work. I have installed all these dependencies, so these are just basically all the libraries, the compiler that you need in order to get running. Okay, so once you have all this, you clone this directory with Git. So Git is part of the dependency, of course. So you use Git like this. Sorry, you won't see me anymore because the browser is in the way. Okay, I will put this bit more like here. Let's do it like more like that. No, we don't see the instructions anymore. So here you clone this Git repository. So I clone into it, and I get all this data on my computer. So this is in my home directory here. That's why there is this little tilde. And if I look it up, I prepared already a FASTA file with our data here that we want to look at, that we want to work on. And this here is of course then the folder that I've cloned here. So I will go into MNHN-Tree-Tools, and then you need to compile it. Now that you can compile it, you have to create a bin directory where it puts all the binaries inside, so all the programs that you then can run. And for that, then I type make all, and then I do here -J and the number of processors that I have on this machine. And this little laptop, I actually have 2 processors, but I have 4 virtual processors. This is hyper-threaded, whatsoever. At least I can use 4 processors. So if you don't know how many processors you have, you type nproc, 4 processors. Okay. So what I do here is, this is very important afterwards, so that you get enough speed, enough bang out of your MNHN-Tree-Tools. So let's get started. So compile the stuff and so make all, use 4 jobs for the compilation. It's faster. See here on my CPUs, my CPUs I already used beforehand because I'm recording all this, but right now I have a bit more usage. It's a very slow machine, it's down because it's very hot here and I don't want it to overheat, so I limit it to 1100 megahertz. Very slow machine. This is a Core M3, this is a little laptop, yeah? Okay. That's the way it is. So here we have our MNHN-Tree-Tools compiled. We go into the bin directory and we see all the tools here at hand. We can run them directly from here. So if I type faster2camere, the first utility that we will use, it's ready to use. Yeah. The stuff is, okay, you can move this bin directory wherever you want, but you probably want to use these tools from any directory where you are in. So I advise you to do something like this, to add this to your path. So what does this do? Is what path? I take the current path variable. Now, what is the current path variable? Echo $path. So this is basically all the folders where binaries that I just want to run from the command line are in. Yeah? So I need to add this directory to this. So how do I do this? I use this export command here on the bash. Yeah? If you use a different shell, you have to look it up. You probably will know it if you use a different shell, how you will do this. So I add the path and I say, okay, I thought PVD, this shorthand for the current directory, does this. If I see the path right now, we see MNHN-Tree-Tools is added. So good so far. Which means wherever I am, for example in this home folder here with my faster file that I've prepared, I can run all these Tree-Tools objects. So if I go up here, I had in my list is faster2camere, no? So what does faster2camere? So it takes my faster file and transforms it to camere sequences, no? So if I look up my Pogo MX fastest dataset, so this dataset of these alpha satellite sequences which are in the gene, which are repeated sequences in the gene that have their own evolution. Yeah. Okay. We just want to use this dataset for our for our demonstration purposes, because it's rather small. It has like, I guess, 26,000 sequences, something like this. And as you see, these sequences, they are like 170 basis pairs long, which is not too long. So if you use the COVID dataset, for example, we tried this with the COVID dataset of 2 million sequences, 30,000 basis pairs long. It takes a bit more time, all the stuff. Yeah, it's pretty fast for what it does, but it takes more time. Okay, so let's get running with this data set here. Okay, put my little editor into background, and I have created here a tutorial project folder, which is empty, and I just will move this Pogo MX faster here to this data set. So this is my input data set. If you want to, let's call this my data, my sequences faster, so that you're not that you're not about this Pogo MX. So it's basically some kind of a monkey which has these alpha satellite sequences. Never mind. It's important. It's data set of sequences of nucleic sequences. Okay. So we have this faster2camere tool here. Sorry, we have exported it, so it doesn't work. What is going on here? Or what did I do wrong here? I haven't been in the bin folder. Okay. Yeah. So normally I shouldn't have done this. I should cd it into the bin folder before I should have done the export. Before I should have done this here. I should have cd'd it into the bin folder, and as I didn't do this, I have just MNHN-Tree-Tools without /bin, no binaries, okay? So we will do this like this. We will fix this rather quickly here. I just copy paste this and add the bin folder, and then it's done, yeah. So /bin. And now I should have faster to come here everywhere whenever they have a folder. How nice, okay? And all the other tools, of course, that are in this folder too. Yeah? So faster file, faster to come here, and we have a faster file. So the faster file is, of course, our my sequences faster file, camera length. Yeah? Remember, when we were here, camera length is basically the k here. Okay, I will use a camera length of 5 to get reasonable. Okay, it's 5 1024 124 k bears. So little 5 mares. We get, if you calculate all combinations of amino acids, you will find out it's 1024. So 5, number of threads. How many CPUs do I have? You remember me running the nproc command? It was 4. You see it here in my little Xosphere indicator here. So let's say 4. Is this a protein sequence, or are these nucleic sequences? The whole stuff also works with protein sequences. It's not really tested. It should work. Okay, use it with nucleic sequences if you want to do something serious for now. Yeah. Okay, 0. So because it's like if 1 0, otherwise so nucleic sequences are 0. What this tool does, it writes all k-mares onto the terminal. That's not what we want, so we use this redirection thing. This is here, this tool here, this little triangle here, which redirects you the output of your terminal to a file. If you're not familiar with Unix, that's the way this should be. And so I tell it to get here, let's say my sequences, let's call it like this, in k-mare form, no? These are 5 mares, no? Because these are, okay, yeah, in 5 mares. Let's call it like this. Okay, let's run this. This runs just with 1100 megahertz. As I said, I slowed down my computer so it doesn't overheat, but it should be pretty fast anyway. So I don't know how many sequences we have in there right now, but I hope it's pretty fast, especially as we create the video at the same time. So let's see what it looks like. So we have the file. Just check how many sequences we have. So how do I do this? One thing you can do this in Unix here is do it like this. If you have a faster file, so basically it counts all the lines where this stuff here occurs. You know how a faster file is formatted. You find out you have one of these 4 sequences is the header of each sequence, and this is just the line count. So you pipe this to the line count, and you get how many sequences you have. 26,000 sequences, 5 mares. I guess we are pretty fast. Just to show you what one line looks like. N1 means one line. From the my sequences 5 mare. I could also open it in an editor, but it's pretty big right now. So, and you see, you get per line, you get the sequence. So first sequence, it's in the same appearance as in the faster file. They are just numbered, but they're the same as in the faster file. And you will see here, this is the k-mare vector. So this is like the 5 mare representation of this sequence here. And if I take, for example, 2 lines, so just get me the first 2 lines as here. On the second line I have sequence 1, on the first line I have sequence 0. That's how this is formatted. This is 1 line. Near the terminal, of course, it breaks it apart, but 1 line. Okay. You get the idea. This is tabulator separated. You can parse this with TSV import, something like this, if you really like to do that. I discourage you to do that. It's just an intermediate file here. Of course, you can use our tool if you want to calculate chimeras. I guess we're pretty fast. If you find a faster tool, then send me an email. I will try to beat them. No? That's the way it is. So, we got it. This is the tutorial. We got the K-mer representation right now. We said, okay, we are on our way to the tree. One next step on our way to the tree is we want to have a PCA. No? Yeah. So we have this K-mer to PCA tool then. And in this K-mer to PCA tool, you see you have basically this K-mer file is the file that we have just generated here with our previous command, and we want to calculate a PCA from this. We want to reduce this, in our case here, to 7 dimensions. Yeah, let's see what this looks like. So here it says, what do I need in order to do this file in? So I need a K-mer file. So the K-mer file is the my sequences file here. No, 5mer. I need a right K-mer to project it. It's basically a PCA, so this is basically a file where you get for the number of dimensions that you choose a value. So 7 dimensions, you get 7 values per sequence, which represent the sequence in your reduced space. That's what you want. So I call this PCA, and I will say set V, because it's on the first 7 principal components that I want to run this. In this case, I use this so that I can remember that the rest, you name this whatever you want, but that's the way it is. Eigenvalues. So eigenvalues, they're important. The eigenvalues basically are the length of these vectors when we remember our little diagram here. Let's remember our little diagram. The eigenvalues give you the length of this here, and they are sorted from the longest to the shortest, something like this. So you can basically find out, well, how much information do I retain, because you can calculate the length of all the little eigenvectors that you throw apart, or the little dimensions that you throw into the trash can, and you can compare that to those that you keep, and then you know how much information you actually retain from your dataset. Yeah, sounds pretty basic. Okay, that's the way we have it. Eigenspectrum. So my sequences.ev eigenvalues. We compute here all the eigenvalues in this little calculation here. We just keep the first 7 vectors, which correspond, of course, to this length, and 7 dimensions. Number of threads that we use. Well, 4. Now we have 4 processors. Nice. Now we don't need to redirect here anything. The outputs are all given. It should run. It takes a bit of time. Let's run this. 26,000 sequences. I'll tell you. I hope your PC. So we did this. We get our principal components, and so what you can use is you can use this GNU-plot program. If you don't have this, you just do apt-get install or yum d whatever your system uses in order to install this. Here it would be emerge GNU-plot, and again to it's this GNU-plot program, and with this GNU program you can do something like plot with these files because they're written in the right story here. And you can say my sequences, so this PCA7V file that I had, and I say using 1 to 2, then I get the first 2 principal components. So the projection into the first 2 principal components. And I get this. This is our the result of our PCA here. And we already see that we have maybe a subspecies here. Of course something here. We get big stuff over here. Yeah, that's the way it looks like. Okay. So this is, so you can already cluster a bit just looking with your eye on the PCA. What is more important here is also that you look at the scales here, so that you know, okay, this first principal component I'm here on -10, ranging from -10 up to 2, so around 12, and here I'm at around 9. Because if this is your 1000, then you have your increments that you use here, so you know your delta epsilons, how much you increase the radius every time. And if these are very large scales, then you should think about what kind of radius you use. So basically the scales here give you a hint for the initial conditions that you want to use during the further tree building calculation. Okay. You also can look at this in different ways, so you can say, okay, I take the first and the third principal component, of course, and then you get something like this. And you can also say, I want to have a 3D plot like that. I will change the terminal type, but I guess with this, yeah, I'll try it out like this, so that's just S-plot here. And then you can say, I want to have the first 3, and then normally you can turn this around here and you get your PCA in 3 dimensions. Actually we calculated it in 7 dimensions, but these are just the first 3. We see that we have here ensembles which are just like loose from this other stuff here, which are going to be clusters in our system probably. Yeah. Okay, we got all that. Okay, that's the story. That's the PCA. Right now we want to go back to tree building. So that's not the whole story about the PCA, because we also have this PCA visual extract tool. So if you wanted to do clustering just by looking at the PCA. So what you need for that, the faster file, the faster input file, and you need your projections file. So my sequences on PCA7V, the number of dimensions we set 7, that's why we have 7V, and just as before, the dimensions that I want to project into. And if I hit enter here, I get a little image like this, and I can go here, I can just draw with my cursor across like this. So I go here, I click the mouse down, and I keep the mouse click down like here, and then like an imaginary rectangle I have selected 1554 sequences. And if I do this here, then I get to 24,721 sequences. So you should think about it, because it's a big deal between 1575 and 1555 and 27,000. So if I say this cloud here is 24,721 sequences, and this cloud here is 1,154 sequences, this is nothing compared to this over here. So these are things that happen, and you should think about this when you look at your data sets. And so, for example, if I want to just see this little little cloud here. So let's have these 1,500 sequences, 1,500 sequences. I just go here, I keep my cursor in here so that this window keeps selected, and I hit enter. And did I specify output file? No, so this will crash probably. Yeah, because if the faststart file is null, so okay, so let's cancel this. We should name a file here, so let's say out faster up. Then we can do this here. JFR 1,500 sequences, and says hit enter to save to out faster. Yeah? Of course, this has to stay illuminated here, so I hit enter here, and right now it's saved. And then I can quit this here, and I can use my editor here in order to visualize the sequences that are part of this little part on the other side here in my dataset. Okay, so you can use this little tool that we have in there. Okay, nice or not nice or whatever you like. That's the way it is. Sorry for that. So we have that here. Right now we are back to tree building. So if the tutorial project and right now we're going to tree build. Okay, so what do I want to do? I want to do adaptive clustering right now. So what I told you about these epsilon differences, and let's just go back to this tutorial so that we get what we want to do here. So we want to do this here. So this is our data set in 7 dimensions if you want to, and we want to build a tree, a phylogenetic tree out of this, and see what this looks like. So we do this. We do this is called adaptive clustering here. As you see, for the different that I've shown you for all the different types of measurements of the length here, for these distance measures, for these different distance measures, we have a different tool here. We use the PCA tool as we performed PCA already. And the Smith-Waterman, well, you can do it on the GPU or MPI on the GPU because it's very computational intensive and takes way longer, so it's implemented in MPI and on the GPU and stuff like that. But that's what you basically want to do is this here. Most of the time it works best. The Smith-Waterman has the advantage that it's more describable, but you look it up in the manual if you want to go into these details or in this algorithmic supplement here. So, adaptive clustering, what do we need for that? So we need a PCF FASTA file, and we need to think about our input values. So we need a FASTA file, we need this my sequences FASTA file first, then we need an initial epsilon value, so it's at 14, 10, something like this, no? So initial epsilon value, what will I do here? I guess I choose 1. Pretty damn. So let's do 0.5 will be fine. 0.5 increment 0.01. That's pretty dark, and it's long up to 14. Can be 1,000 steps. 4 cores. I can do 4 steps at one time. 26,000. I have to do 26,000. The 26,000 comparison each, and it's pretty much to compute. Well. It's something like this. Minimum numbers of clusters in 2.5, like that. Minimum numbers of clusters in epsilon. Let's say we want to have at least 3. I can do 4 here. Let's do 4 here and 5. I'm not sure. Not 5 in this case here. 5 is 5, fine. Why not? Let's do 4. Okay. Path and prefix. So I want to create a a file which I call layers. So basically what it stores there are the 3 layers, you know. So what happens here is, so that you understand this, is you get, these are the layers. For each layer you get a file that contains the clusters inside. We call this the split set file. So you will find tools in the MNHN-Tree-Tools which are called the split set, whatever. So these are the tools that you can apply onto these layers. Yeah. So I will call these layers, and I will say I want to store this to layers /L, and then they put the number behind it, and that works pretty decent here. Layers L, pass and prefix of split set files, layers L, prefix L. Okay. Number of threads to use. How many threads do I want to use? So 4. I only have 4 cores here, 4 virtual cores, 2 cores, 4 virtual cores. Number of threads to use. Dimensions in the projection file. 7 dimensions we had there, and we need the projection file. Well, what is our projection file? It's this PCA file. No, my sequence says PCA is 7 vectors. And what you want to do is you want to redirect the output, because there are tools which can use this output. It's basically just a log, and I will call it adaptive log. It's a log file. It's very interesting stuff in there that we will go through once this is finished. And we run this right now. It charges the files. I found once, and then you see that you have here the stuff running. 4 cores. We won't overheat. Hopefully. I've clocked it down. You see it stays at 60 degrees. Pretty fine. Okay. So valid. So we have these layers. We do a TBScan for the little epsilon. Sorry for that. The little epsilon. Then we increment 0.5 in each step by 0.025. We have 4 in the radius. So each we perform a TBScan hundreds of times. Okay, each times at a different epsilon value. So 0.5, then 0.525, 0.55, the next one, and for each those we calculate the clustering. Yeah. Okay, as we did this here. Each time we do this for different radiuses, which grows and grows and grows and grows and grows, and as this grows here, of course, the density dilutes, and it basically we get forced for the lower, something like this, then something like this, then the final we stop and we just get one cluster, because then we say, okay, the stuff is finished. Yeah, like here right now. Yeah. That's it. So let's look at our log file. Let's open it in Emacs. It's more handy here. Make sure you see me again. So what do we have here? We started with 74 clusters, okay? That's what we found at the initial set obtained. So we started with the epsilon of 0.5, we increased with 0.2025, that's what we put here on the command line. We get an initial set of 74 clusters, so forced clustering, 74 clusters, and this density given with 0.05 epsilon value. Yeah. Coverage is basically how many points are actually in the data set. So the story is like, if you build these clusters remember here we had these 2 points, these points, all of these other points here were outside. Okay, that's the coverage. So what's that percentage of how many points are basically part of the cluster in my data set? If I have very dense clusters, okay, then you don't have a good coverage and you might lose out. So the story is, if this here is 0.0 something here at your initial point, forget it. Yeah, reduce your epsilon. Yeah, 0.04, 0.036 is just at the limit. That's just fine to start with. Yeah, 0.5 might have been probably better. Yeah, because then we have here coverage 0.5, and we see as the density dilutes, of course, the coverage gets better. Yeah. And we see that the last cluster, so there are still points that are somewhere in space that are not covered. They're outside the coverage, and outliers, wherever they are. Do you see that here? Yeah, that's the way it is. So at the last stuff, we have like 4 clusters that go into that, and that form just one cluster, and that's the way it works out here. And here basically you see this, how these clusters are connected, and you basically from this log file you already could, in theory, with these connections that you have here, build your tree. Yeah, by hand if you want to, but we have a tool for that, of course, which does this fully automatic and which doesn't use this file. But you see here that how going from layer to layer, how you get these connections up to layer 19 here, and how many clusters you have in there, and how they are connected to the previous layer. Okay, that's what you all have in here, and this is very interesting because here you have basically the layers, and with each layer you have epsilon, which infers your density in 7-dimensional space. So it's a radius in 7-dimensional space, don't forget that. Yeah. So it's not linear, this epsilon dependencies, because the density is the volume by the number of points. So it's a factor 7. It's not like, yeah, okay, 7 dimensions. Yeah, and you see that not all in steps are caught, because if the number of clusters doesn't decrease, that's what I told you before, we don't get the new cluster. Okay, that's how this works. So once we have this file, we already basically have our tree, but right now we want to visualize it. So how do we visualize it? We have a tool which is called split sets. So I told you about this split sets. So split sets is what we have here in layers. So all these files, L00, these are binary files, and so they are written in binary form, and we call them split sets. So they store all these cluster information for one layer of the tree. Yeah. Yeah. So we have a tool which is called split set. It's nucleic. So, and then you get a nucleic file, a dodecanogram, that you can visualize with a nucleic viewer. Yeah? So you find nucleic viewers on the internet, so even online, I guess, even in the browser, you can visualize these nucleic files. I will show you how to do this with the nucleic tools, so I strongly suggest you that you download the nucleic tools. Nucleic tools, I guess, yeah. Nucleic tools, no, nucleic utility, nucleic utils, it's called, nucleic utils, from the University of Geneva, yeah. Here you have the tutorial, that's the good one here. But you will find nucleic utils, it comes from the University of Geneva, so Uni Genève or something like this. and it always brings us back to this one, but you will find it for your distribution. It's in most of the distributions. To apt-get install nucleic utils, something like that, you will find it. Yeah, not the conda one. The real C program, something like that. Yeah, not the, well, yeah, okay, whatever. So you have this split set nucleic, and with these nucleic tools, I show you how to visualize this in the form that we work it out. So as I told you, we have here a filter for small clusters. Don't use this, okay? If you want to filter your, what this basically does, it all nodes which have less than a certain number of sequences, they are thrown out. So here the nodes, of course, they have at least 4 sequences, because we did this with this 4 here when we performed our adaptive clustering. Where is it? We put in here 4, so we have at least 4 sequences anyway. But the problem is, so if you do this here, the annotations of the tree won't work. Yeah, you get a correct tree, but if you annotate the tree, I'll let it annotate by these 2 or 4s. So if you want to filter beforehand, we have a filter program which is called filter, or something like this, filter split sets by min. So what this does is create here new split sets, all these clusters. You look it up in the manual. Yeah, and you use this tool in order to do this correctly. To basically to create a new set of files where you throw out all the clusters which are smaller than which, let's say, contain less than 10 sequences. Yeah, okay. We won't do this right now, but just to tell you, don't do it in split sets nucleic. You will get a nucleic tree, but the annotation will be wrong. It's hard to fix, so probably won't fix it. It's just a visualization tool, so if you want to get a correct annotation, don't do this. Length from output file. So you can use this output file, this log file that I told you. It takes the different epsilon values from this log file, and then it creates your length from the tree branches. They have then the length corresponding to this epsilon value. Yeah, not just the epsilon value, so it really calculates the volume difference, so that this length has a meaning. And yeah, you can do this in L1 density, in hypercube, and in hypersphere, and things like that. Yeah, we won't do it here. Here we just want to give you an overview of the tools, and we just want to build a tree, because if I do this here, I will get maybe very long branches, and it will be very difficult to read and stuff like that. You can do this. You give it a try if you want to, and for demonstrational purposes, I won't do it here right now. Dimensions. So yeah, so if I do this here, of course, in order to calculate this hypersphere and hyperfocal group, I have to say you have 7 dimensions, so I would have to put 7 in here. Out file, yeah, this is the out file. If you do this, yeah, that you have to show the log file basically, and this is the min points that you've used so that you can get this density correct. We all don't need this, we just want to give them the clusters, and each length basically for it's 1 then between all the clusters. It doesn't matter. This is just for demonstration purposes, so we wanna get through this tutorial here. Yeah. If you want to do this, if you want to have lengths which correspond to evolution, and if you want to measure the length and infer an evolutionary distance in millions of years maybe, then you can do this. Yeah, look it up in the manual, we have it. Yeah. So we do this here, split sets. Let's get started here. So we have our what do we need? So we need we need no filter. We need no lengths from output files. and we want to have our files here. So these are the split sets. So this is layers L, and here you can put the star, yeah, because the way they are numbered, if you use bash, maybe in another shell it won't work, I'm not sure about that, but if you use bash or in decent shell, in any decent shell, the way it's numbered with the zeros up front, it correctly puts them in correct order here. You just put the star. If you put them in a lone directory, you can do this. That's the way to do it. Yeah, okay. If I do this, I will get a nucleic file. And this nucleic file is written to my terminal here, so I have to redirect the output. And I will call this my tree .dnd. Yeah, .endogram, that's a nucleic file. Okay, it does this. Then if I do emacs my tree, I get the .endogram. Okay, that's a nucleic file. If you know about the nucleic syntax, if you know how a nucleic file works, that's the way it looks like. Yeah. Okay, here we get 1 everywhere because we didn't rescale our length. Okay, so in the tree, the distance between one layer to another layer is 1, and not as we said we could relate it to the evolutionary distance. Yeah. Okay. We have a nucleic file, and right now we want to visualize it, so this nucleic tools, and the tool here is that you need is the NW display, so this part of these nucleic utilities that I've shown you before, tried to show you before on the web. So if you go here on this Buster site, I guess this is the correct tools, yeah, so this is the manual of it. So these are the guys who did this, who made this, just a visualizer of this .endogram files. Yeah. Okay. Perfect. So nucleic tools, and we display. And what you want to do here is you want to have a SVG file. You might want to have a radial SVG file so that you get a nice circular .endogram stuff here. You want to use a pretty large width, so I will start with, let's say, 1000, so that you can read the labels on them. And then you want to suppress certain labels, so this is opacity 0. This basically what suppresses this is this length indicator. So basically the length at each branch, and it would write the length across each branch, and that's what we don't want to have. We just want to have the label there, what kind of cluster this is, okay? And once we have this here, well, we put our .endogram here, and this would create this SVG file, and that's what we need, so we will call this our tree in SVG form, scalable vector graphics. That's the way it is. And we run this, and this was pretty quick. Crazy tree. So we have our tree in SVG form. Okay, to visualize this, you could open this up in Inkscape and you get your tree, and I like to have a PDF to open it up in NVINS, so I use RSVG. So if you have RSVG, which probably you have, if you don't have it, you do apt-get install RSVG, you find it somewhere. So there is this RSVG convert utility, and F, you can define a format which is PDF in my case, and I want to do my tree SVG, and this basically converts me the SVG to a PDF, so my tree.pdf, and does this, hopefully correct. And right now I can use my PDF viewer, which is called Evans here on this machine, and I have my PDF and the tree, and I see that I can read nothing because I have such a big tree that I don't see the annotation. Okay, so we will increase the size of the whole stuff here. So this is basically this W number here, which tells you how large you want to have it. And make this here, let's say 2000, 2500. We create a new tree, We transform this with RSVG convert, and we use Evans my tree PDF in order to visualize the tree. And right now we can say, okay, this is pretty well annotated. And so you have for each node here on the edge, and even here on the inside, well, here on the inside it's a bit less readable, but you could increase this with this W parameter even further. You see for each node a certain identifier, which cluster this is. So let's make this a bit, let's zoom in here. I hope I can drag here. Yeah, I can drag here, that's great. If you see this here, so you see, for instance, this here is one cluster. This is the cluster of the next layer. Yeah, so we have layer 0, layer 1, layer 2, layer 3, okay? Layer 4, okay, which merges all these clusters here into it. And here this is the number of sequences. So this is layer, cluster, number of sequences, okay? Layer 4, cluster 0, number of sequences, yeah, 16,000 sequences, okay? That's the way it is. And then you get to the center, where of course we have layer 19, so we have 19 layers in our calculation here. Cluster 0, there's no sequence number because this is all the sequences. Basically, this is the story. It should be. And for example, here I have layer 14, cluster 0, 22,915 sequences. Okay? Okay. And here, somewhere we should have the fan between the little thing and the big thing here. Just thinking about it, should be probably this here should be the second part here that we have seen on the shore here. It starts at the cluster layer 4, which is basically the second island, if you want to, yeah. But never mind. Okay. So these are basically all your trees, and what you want to know is that on the outside these are the most dense clusters. As the more you get on the inside, the less dense you get, the earlier you're in evolution. That's the idea how this should work here. And the question is right now, how can you investigate this? So how can I, for example, investigate? Well, there are also tools that I won't show you here in the tutorial that you will look up in the manual, that allow you, for instance, to create a tree that is colored there, so that you that's in the tutorial and the manual, that you basically can say, okay, I have here a sequence in my data set, and I want to know where this sequence is, and it can create you a tree where basically it lights up the whole path where this sequence has been discovered. You can define a whole cluster and color this, degrade it, and stuff like that. All things that you can do. Yeah? For that, look up the manual, look up the tutorial in the manual. This here should be just an introductionary tutorial. Yeah. What I want to show you here is, well, many people ask me, well, we have these nice trees, but how do I know which sequence is where? And so, for instance, okay, let's say I want to find out all the sequences that are here in layer 15, cluster 1. Yeah, so each node has this identification. So layer 15, cluster 1. Okay, 588 sequences. Okay, let's do this. As I said, layer 1, layer 15. What was it? Layer. Sorry for that. Forgot it. Oh my god, it crashes because this PNG file, these PDF files, they're so big. What will I do with this? I kill you, come on. Delete. Doesn't work. Destroy. Okay. I stopped it. My fault. I stopped it. I should just have put it into background. Let's open it up again. Nobody knows what's going on. Come on, open my file. It's my tree tutorial that still works. Let's do this correctly here. Okay, it was somewhere running still, whatever. Maybe a log file or something like this open. So where do I want to go here? I want to have my, let's try it at this one, maybe layer 15, cluster 1, okay? So as I said, so how do I find out which sequences are where in the tree? So with these little indicators I can find that out. So if I don't want to have these indicators with this nucleic display, you do here B opacity 1, you do minus I opacity 0, then you don't have these indicators here, and you just draw your tree and stuff like that. But that's all described in the tutorial, and whatever, in the big one, in the big one in the manual. This just should get you started here. And we have here a tool which is called split sets. Split set to faster, something like this. Okay, a split set to faster, split set to faster. That's what I want to do. Yeah. Okay. And this basically does what I want to here, because I mean, I said layer 15, so as I told you, I stored my stuff here in layers, so layer 15 corresponds to layer 15, of course, so what I can do is split it to faster. And I can do layer 15, L15 in this case. And path and prefix where the cluster should be stored here. I will do this into the temp directory because I don't want to create a directory now, or let's create a new directory here. Let's create a new Encoder. Let's say clusters from L15, okay, from layer 15. And then I can do something like this, split it to faster, layers L. So I need the faster file first, so the faster file is my sequences.faster, the file containing the cluster set, so this is layer 15. And prefix, so clusters from L15, and I say C here, okay, big C, let's do it like that, and then it ran. And if I go now to clusters L15, I have C0 to C11, and what I wanted interested was layer 15 C1, and there I have 588 sequences that merged from all these sequences here, from those here, and from this branch here, basically. Yes, all these little ones here, they merged into it. This here seems like something, and yeah. And when I do this here, I can do Emacs C10111, and I have the faster file of these 500 sequences. Just to verify that. And you have those 588 sequences in this faster file here. Okay. And that way you get all your sequences in the different clusters, you know, what each sequence is and stuff like that. And there are several tools that you can trace sequences through the tree and stuff like that, and look it up in the manual. That's basically it for today. I hope you understood how MNHN-Tree-Tools works, how you might use it for your purpose, and I hope you found that this tutorial could help you to get it set up, to get it run, to investigate your faster set with MNHN-Tree-Tools, and to infer phylogenetics with our tool. Thanks for going through this tutorial with me. Bye.